So let's talk about a physical property of halogen and alkanes, and this is going to be how they interact in terms of the electromagnetic forces. Now, this can get a little confusing, a little weird, so let's kind of step through it little baby steps. In order for us to create a dipole-dipole interaction, which is stronger than a dispersion force, which is what we see with alkanes, what we have to do is we have to have a strong difference in electronegativity between the carbon and the atoms bound to. And we see this with all halogens. Halogens are better at taking electron density away from carbon because typically most of them are more electronegative. Now, this may imply to you then that halogens are automatically give us sidepole-dipole bonding. This isn't necessarily true. The big thing the halogen is going to do is it's going to break up the symmetry of the atoms around any carbons. So if we look at this thing like this, 2-chlorobutane. So the chlorine here is going to create a dipole-dipole interaction. So this carbon-chlorine bond is really polarized, and if we get the molecules next to each other, these carbon chlorines are going to line up so this way they interact. And we will see dipole-dipole interaction. But if we look at something like this fluorobutane, this fluorobutane is a nonpolar molecule. It's still going to work by dispersion. So what's the difference? Well, the difference here is that here all the hydrogens are replaced with fluorine. So again, we begin to see this symmetry again. It doesn't really look like there's any breakup in the electron density, whereas if we look at something like this molecule, we definitely see a part of the molecule where there's an asymmetry. You have carbon, hydrogen here. Carbon's taking electron density away from that hydrogen, but then losing it again to chlorine. So we will get dipole-dipole if we don't have complete replacement of the hydrogens. But if we would completely replace the hydrogens with all the same halogen, we'll be back to a dispersion force. Now, the other misleading thing about the changes in the boiling points of halogens versus pure alkanes is that there is a weight factor to it. So chlorine is 35.5 AMUs. So it's going to weigh 35 or 36 AMUs depending on the isotope. Because of that added weight, we do look like we're increasing the dispersion forces simply because the molecule just weighs more. So in general, halogens have two effects on changing the boiling point of the alkane that they're in. If they're just by themselves, so we don't have 100% substitution, we do start seeing this dipole-dipole interaction, and this dipole-dipole interaction is what's going to give rise to their higher boiling points. Now, we are also seeing the effect of adding the weight as well. Because halogens weigh substantially more than hydrogen, they're going to look like they're increasing the strength of the dispersion forces. So even if we do something like complete 100% substitution of all the hydrogens with the halogen, we'll still see an increase in the boiling point, not because we're seeing dipole-dipole bonding more, but just because we've added so much more weight, it looks like the dispersion forces have gotten better.